Okay, hello. We're going to talk about forces of friction or friction forces today, or right now. And friction at a near microscopic level is caused by all these little electromagnetic interactions between the atoms and the two surfaces that are in contact, and the collisions between all the little imperfections and ridges and valleys in the surfaces of those materials. Which is a complicated physics problem, right? If you wanted to figure all that out and add them all up and figure out what the total force of friction is when you are, putting an ice skate blade on an icy pond, or pushing a box of books across a room, or dragging a sled across snow, well, this would be a tricky physics problem if we didn't have a nice, simple model that took into account all of these things, at least at an approximate level. Okay? And that's what we're going to do here. And we can split the types of forces of friction into two: kinetic and static. And the names imply a lot about what the situation is in each one of those situations where you would have kinetic versus static friction, but let's lay it out explicitly. So say we have an object and we have a couple of slopes, and in one case over here it has a velocity. It's sliding down the slope right here. And if you have this situation where the surface of this block and the surface of the ramp that it's on are in contact and they're moving relative to one another, then the force of kinetic friction is relevant. And in the case on the right, so over here, well, we have a stationary object, not accelerating or anything either, and it's being held in place as gravity tries to drag it down the incline. The force of static friction is opposing that attempt to move, okay? So in both cases, you either have movement or an attempt to move the object. And whether or not you're talking about kinetic friction versus static friction depends on whether you actually are moving or whether you are stationary and remaining so. All right? Now, like I said, the mathematical model for figuring out all these microscopic interactions that add up to give us the forces of friction in this case is tricky. But we've got a nice simple equation that's going to give us these forces of friction that we'll lay out here in just a moment. But first, let's take a look at some of the forces that are acting on, first, the kinetic case. So we know from our last lecture that we have a force that is normal to the incline, right? Normal to the surfaces that are in contact, so F sub n. And we have a force of gravity that is acting straight down, okay, pulling towards the center of the Earth. And the one that we're adding here is that there must be a force of friction, a force of kinetic friction in this case, that is opposing the direction of the velocity. So I'll call it F sub F. You're free to call it, F sub K, which we're going to do here, okay? If you want to be more specific about it being kinetic friction. But that kinetic friction force, so again, so you've got your F sub K, you've got your normal force, okay, and that F sub K is going to be equal to the product of two things. One, the normal force that this object is experiencing because of resting on the inclined surface, and this parameter, which we haven't encountered before, and it's the Greek letter mu sub k to indicate that it is the kinetic coefficient of friction, sometimes said the coefficient of kinetic friction. Either way, it's fine. Okay. And what that is just a proportionality constant between the size of this force acting on the object and the size of the resulting friction force. And this should make sense, right? For example, the whole idea behind a spoiler on a car is that as you go faster and faster, the spoiler acts like a wing and it presses the tires of the car harder and harder into the ground, which gives you more friction between those tires and the ground, which then allows you to go faster around curves and things like that, right? To maintain grip. That basic proportionality, the idea that if you are pressing down harder on the ground and thus the ground is pressing up harder on you, that should be proportional to the amount of friction force that you feel, I think is reasonably intuitive, right? Now, the kinetic coefficient of friction, well, if it's very, very low, that means that you've got two surfaces that are quite slippy relative to one another. You could think about this as like an ice skate blade, so a piece of metal on a piece of ice. All right, that would have a relatively low coefficient of friction. If you had a gym floor, but a gym floor that hadn't been dusted in a while, so you had a bunch of dust over the top of this polished wood and you went around and you tried to run around and play some basketball there, well, you would find out that the coefficient of kinetic and static friction, as it turns out, would be really quite small. It would feel like an ice skating rink. So slippy surfaces, okay, have relatively low coefficients of friction, and ones that have a lot of friction have relatively high coefficients of friction. And the coefficient of friction is just dependent on the materials, right? Those surfaces that are in contact. So if they're rougher or if they're made out of one substance like aluminum or steel or ice or snow, the identity of the two surfaces in contact, so we might have like, maybe this is a wooden block and the surface is metallic of some kind, okay? And so you would have some coefficient of friction that would model the strength of the force of friction that occurred for a given normal force, okay? Now don't mistake the coefficients of friction here with the force of friction, right? Sure, one is dependent on the other, but the coefficient of friction is just down to the identity of the surfaces that are in contact, all right? And how big the force of friction is dependent on that thing, that coefficient, times how big that normal force of the surface acting on whatever object is. All right, so that's the kinetic friction case. And we have this simple equality that shows us exactly how big the force of kinetic friction will be resisting the movement of that object over that surface. Now, in the static case, well, we've got a similar set of forces, except all these forces we know must be adding up to zero because we have a situation where this object is stationary and it is remaining stationary until we change something about this situation. So because of Newton's second law, we know that if this thing is remaining at rest, this is going to be zero, and so the net force, so the sum of this force, and this force, all has to go to zero once you do it vector-wise, okay? And the equation, inequality that describes the size of the force of static friction, this guy right here, okay, is very reminiscent of the equation we have over here on the left for kinetic friction. You've got the normal force again, you've got a coefficient, in this case it's the coefficient of static friction, and the only difference is this bit right here. And it's worth exploring that a little bit. Why is it an inequality rather than an equality? Well, if it was an equality, well then the force of static friction would always exist. Well, an incline, for an object that's stationary, that is. On an incline, that doesn't feel weird because we know that there's, some little portion of gravity is trying to accelerate, right? That component of gravity right there is trying to pull this thing down the incline. And the force of static friction is opposing that. And so it's there, and that all cancels out, and things make intuitive sense, line up with what we would expect from the real world. However, Imagine a situation where instead we have the block sitting on the ground, okay, like this. Okay. And it's stationary, right? Say it was stationary, same kind of situation that we were describing here and here. Well, then, if this was an equality, then it would be telling us, oh, well, there's some force of static friction acting in some direction, but it's a little hard to know which one, because remember that this force of static friction opposes the attempt to move. Gravity here is trying to drag it down the incline, right? And the force of static friction is opposing that attempt to move. But when you've got an object on a level piece of ground or on a desk or something like that, you don't expect it to have some horizontal force that always exists on it because there's no attempt to move. And so to build that into mathematics, we have this less than or equal to sign. Now the maximum value, so Fs max, say, is going to be when these two things are equal. Okay? And if you were trying to get this thing moving with, say, a push or something like that, well, then you would have to overcome this, this maximum static friction. I don't know why I put in two equal signs. Get rid of that. Okay. And of course, the minimum value, as we just discussed, is 0, right? If you have an object that's not, you're not attempting to move it, nothing's attempting to move it, gravity is not pulling it down the incline, nothing like that, well, then there's just no static friction until you make an attempt to move that thing. And so the actual size of the force of static friction on something can vary between these two extremes depending on how much of a push there is, or pull, trying to dislodge it from its state of rest. Okay? So one last thing about these forces of friction and coefficients of kinetic and static friction is that this is always the case. Now, sometimes they're pretty close to equal, okay? But what this is saying is that the coefficient of kinetic friction is always a little bit less, or sometimes a lot less, than the coefficient of static friction, and that friction is always parallel to the surfaces in contact. I've kind of done that by implication, drawing the forces of friction as I have here. But like the normal force being perpendicular to the surfaces in contact, the kinetic friction and the static friction forces are always parallel, and they're always opposing either the motion of the object or the attempt to move the object, in this case by gravity, down the slope. The stipulation that the coefficient of kinetic friction has to be less than the coefficient of static friction comes, I think, is relatively intuitive. If you've ever tried to move a heavy object and then keep it moving, you know that generally speaking, you really have to give it a big shove, sort of throw your shoulder into it to get it going. But once you do have it moving, it takes considerably less effort to just maintain that velocity, okay, unless you let it stop again. And that's sort of the idea behind this. There are certainly more technical reasons why this needs to be the case, okay, but that's the basic idea, and we'll mostly stick with that hand-wavy version of the explanation. So I hope this lays out the basic characteristics of forces of friction for you. And we're going to come back next time and talk about an example that just shows how all of these Newton's laws and friction and normal forces and things like that work together to bring us to kind of a counterintuitive conclusion. So I'll see you then.